Everyone is doing great. Today we are going to implement polarization transforming metasurfaces. Since I have mentioned earlier that the blockchain metasurfaces are C4 in symmetry, similarly the polarization transforming metasurfaces are either C2 or C1 in nature. So here is one of the papers on multifunctional polarization transforming metasurfaces. So we are going to implement it. I have downloaded this paper. Here are the design parameters that are given, and these are the results which we are going to extract in the CST Microwave Studio. I'm going to open CST. I'm going to design this unit cell, and is going to make the results as well. Okay, since I'm designing unit cell, I'm going to select it. Phase reflection, then frequency. I'm going to select it later as well. Okay. Right. First, I have to design substrate. So what are the parameters of the substrate? Since the substrate is FR4, uh, okay, and the thickness of the copper is also given. The height 2.4 mm. Okay, that's the 2.4 mm substrate, and the length and width of the unit cell are given in the P. Where is the P? Okay, here's the 8.25. Okay, now we are going to design it. Okay, I'm going to say minus P by 2 into P by 2. I'm writing P by 2 here because if it's gonna from 0 to plus P by 2 and minus P by 2, it's gonna go cause the P. If you can go it either like 0 to P by 2 or minus uh, 0 to P or minus P to 0. It's totally up to you. So I prefer this way because it makes calculation much simpler for me. Now it's the thickness of the substrate, right? And what's the substrate? It was upper 4. Yeah, that one with the thickness of 4.3. What was the thickness over there? Sorry, not thickness. That was for the permittivity. It was the 4.3, right? Okay. That was the upper 4 that they have used. Okay. That 8.25 mm. Okay. What was the substrate height? That was about 2.4 mm, right? 2.4 mm. Okay, it's this is the substrate of FR4. No, this is FR4 substrate, and the unit cell of the design structure is going to be designed on this surface. Since it is completely reflective, so bake should be grounded. So I'm going to ground this. Okay, minus P by 2 to this. Uh, since this thickness of the copper was 0.035 mm. Okay. Oh, sorry, it was copper. I assign interior and color. That should be the. I'm gonna put it from here. Copper. Okay, that was this pixel color. Right. Okay. Now I'm going to design the structure here. So what I can see here first is this is the uh, this is one of the circle. and inside this circle we can subtract something. I can just see the radius of the circle. I can first go to design the circle, right? What's the radius of the circle? That's the 3.5 mm, right? So I'm going to design a circle, okay, on the upper side of the substrate. So material is copper, fine. I have to design on the substrate and have to give the thickness of the T, right? That's 0.035 micron, 0.035 mm, right? That's 35 micrometer, right? Uh, what's the R? That was 3.5 mm. Okay, 3.5. Okay. Now, what next step I'm going to do? I'm going to design this uh, this rectangle, right? Its length and width are given. The length is 5, right? And the width is 3.5. Okay, I have to design a rectangle. Its length and width are given, right? Now you can see its length is I can just go for without giving these variables, but at the end you have to go for the parametric sweeps as well. You have to go for switching the frequencies, so it's better to give the variable instead of giving the specific values. Okay, and so the width. Okay, again it's only substrate. So since the copper is already selected, I'm gonna 5 and 3.5, right? Going to be length 5, and it's going to be 3.5. Oh, sorry, what I did. Fine. Now, I'm going to rotate it, right, to 45 degrees, like this way. You can see here it's up approximately on the 45 degrees, so I did it in the same way. Now I am going to subtraction. Okay, what I did, I just subtracted that into this one. Now I have to go for that one. So what I can do is, that's the uh, what's the spacing over here is D. So it's very simple. I can go for like I can go for minus d by 2 into d by 2, and from 0 to, I can say something like maybe I, let's see, right. Maybe it's okay. Sorry. Instead of this, I can just go with the v by 4, maybe something like that. It's the d. Okay, that is the d is this one, and which is 3 mm. Hmm. It maybe p by 2 is better, I guess, because I just have to give a card, so that's fine. Okay, now I have to rotate it as well. Transform, rotate into 45, right? Okay, Now, what I can do this, I just test this one, right? So I have designed the unit cell according to the given parameters which are here, and now I have to check that the sweep frequency is from 4 to 20.5 gigahertz. So I can select the frequency simulation just 4 to 20.5. So I'm gonna simulate it. That's fine. And I'm going to simulate it. So uh, since the simulation is completed, so we can see the result here. This is the R y into R xy, right? So this is what, and the other max, this is our xx, and this is our uh, yx. So it's the both are the same. You can see both our xx is equal to our yy, and these two are same, and these are same as well. So uh, now we can calculate the PCR since the S parameters are matched. So it's we can calculate the PCR from here on the mixed standard results. Okay, what here I can calculate this. Okay, uh, I can go for mag. So this is our xy, and this is our yy. And what is the formula of the PCR? It's the magnitude of uh, our yx squares divided by our uh, xx square plus our xy square, or either it's the opposite as well. For instance, this is the r xy, and this is the r yy. So I have just put in the formula over here, and now I can go for evaluate. Okay, let's see. It's 20.5, right? Perfect. I'm going to show the formula that I have used for, if we have mentioned the formula, I think we should have to. Yeah, this one formula, like I have used rxy magnitude squares divided by rxy plus ryy magnitude squares. So that's the formula I have used for PC, or it's the opposite as well. As well, it's for the same for our yx and our yx square plus our xx squares. So just the same for both. Since the go and cross are same, so the PCR ratio would be the same for the both. So here's the PCR. No, there's no PCR. PCR. So here's the PCR, right? So here's the PCR that we have calculated, right? So it's approximately same. You can see, not approximately, it's accurately same. You can see this result. So similarly, instead of ellipticity, you can go for the axial ratio.